Okay, so this is chapter 4, lecture 5, the last lecture in this chapter. And we'll be talking about something called titrations. And now titrations, a titration is actually a technique in chemistry, which is extremely important. It's done all over chemistry. It's done with many different type of reactions. But essentially what you're doing, you have a known solution, and using that known solution, you try to determine an unknown solution. And we're trying to determine the concentration of the unknown. So if I know a known concentration of acid, I can then find out an unknown concentration of a base. Extremely important technique, and we'll introduce it here. We're actually going to perform a lab using this technique. So here I'm going to talk a little bit about the setup. So we'll have to use something called a burette. This is a device that's able to dispense precise amounts of liquid, and we'll learn about how to use this in the lab. And then you can actually, it's graduated, so you can actually take readings and find out exactly how much you're going to add. So in here, you would put your known solution, sometimes called a standard solution. So standard means, you think about known. We know the solution. And we do that to find out your unknown solution. So this is your unknown. And what you'll find out is, as you see, our unknown is our acid. So we're going to dispense a volume of that acid. This is actually something called a volumetric pipette, which we'll be using. So we'll pour a bunch of acid in the flask, and then we're going to see how much base is needed to completely neutralize the acid. And then, at that point, we'll be able to use the amount of base that we've added and the known concentration of the base to find out the unknown concentration of the acid. This essentially will be a molarity problem. And the way we're going to know exactly when to end is we're going to use something called an indicator. An indicator will indicate to us exactly the when the reaction has stopped, and so that we know we can then proceed to calculate the concentration. And usually it's an indicator that's specifically designed to change exactly at the end of the reaction. So let's review some of these terms. So we've actually talked about your standard solution is the one of known concentration. The equivalence point is the point at which stoichiometrically equivalent quantities have reacted. So what this means is this will have to relate to your balanced equation. So if hydrochloric acid were to be reacted with sodium hydroxide to produce salt and water, how about this? To produce salt and water, what we know from the balanced equation that the stoichiometry is a 1-to-1 stoichiometry. So we stop whenever 1 mole or an amount of acid exactly has been neutralized by that amount of base. So the indicator is the dye that changes color. Many of these indicators actually are prepared just precisely for that reaction. And then the endpoint is when the indicator changes color, and you know that your titration is finished. So the term endpoint and equivalence point actually look very similar, but equivalence point refers to the reaction, the endpoint refers to the actual experiment. You're hoping that your endpoint is at the equivalence point. That's the idea. So the endpoint, catching the endpoint, is a matter of picking the right indicator, and there's a few details which we'll talk about a little more in the future. So here is our problem. We're actually going to do a little problem here. So suppose we know we know the molarity of a sodium hydroxide solution, and we want to find out the molarity of an unknown hydrochloric acid solution. So what we know is molarity of sodium hydroxide, and we know how much volume. We can actually add any volume we want of our unknown acid. We can measure that volume easily. So we take a volume of the HCl, and then we measure how much sodium hydroxide was used to neutralize the HCl. And then from that, we'll be able to find out the molarity of the HCl. And that's kind of the idea. So let's try this example. And the example is 25 milliliters of an unknown concentration of hydrochloric acid was titrated with a standard solution of 0.100 molar sodium hydroxide. 47.5 milliliters of sodium hydroxide was required to reach the equivalence point, and what's the concentration of HCl? So technically this is our setup. So what we'll do is, let's go ahead and find out from the added sodium hydroxide exactly how many moles of sodium hydroxide were added, because however many moles was added of sodium hydroxide, that's exactly how many moles of acid was reacted. That's the idea. So our moles comes from the molarity equation, which we've described earlier as being liters times molarity. Again, this is molarity is moles over liters, so we're just moving liters this way. And let's go ahead and, in this case, we'll multiply our liters, and our liters is actually, we have 47.5 milliliters, so we got 47.5 mils, and converting this to liters is, again, we can do a little conversion. Let's move the decimal left 3 times, and 0.0475. This is actually, again, a little bit of a shortcut. We can convert from milliliters to liters, hopefully, by this point. So let's go ahead and multiply liters times molarity. So we got ourselves 0.0475 multiplied by our molarity, which is 0.10, 0.100, and we get ourselves an amount of moles. Essentially, we divide by 10, so we got ourselves 0.00475 moles of base sodium hydroxide. Now, if this is how many moles of base it took to neutralize the acid, that means we had exactly that many moles of acid in the flask. 475 moles of HCl. Now these are the same because, again, stoichiometrically from the balanced equation they're the same. So if you take a look again at the balanced equation, it's a 1 to 1 mole ratio. That's why those are the same. So now, knowing what the how many moles of acid we have, we can find out the concentration of the acid because we've measured the volume of the acid that was in the flask. So now for the second part, we could take, so now we need to find out the molarity of the acid. Again, molarity is moles per liters. So here's our moles. This is our moles. So we got ourselves 0.00475 moles divided by how many liters. We're told that we actually used 25 milliliters of the unknown. So 25 milliliters, 25.0 to be exact. Again, if we divide by 1,000, we get 0.0250 liters. So let's divide by that. Go and divide those two numbers, and we get ourselves a value that's very 0.00475 divided by 0.025. We get ourselves 0.19 for the answer. Using significant figures, looks like 3 significant figures, so we'll put a 0 at the end here. So this is our molarity of our hydrochloric acid. And so, a bit messy there, we'll try again. This is our molarity of our hydrochloric acid. So this is a technique in which we can find an unknown concentration using a known concentration, which is in this case. So we'll actually do a number of problems using that. Alright, and that concludes our not only Lecture 5, but also Chapter 4.